Hi, everyone. I'm Austin Schuh. I'm one of the mentors on 971. I'm our software mentor, one of our software mentors. So what we're going to do is we're going to program together. We're going to program this elevator together. So if you can't, we need to be able to see the whiteboard or see the display over here. In our last session, we developed a physics model for our elevator here. Okay. So now what I want to do is I want to program the elevator using our model. So we're going to do what's called test-driven development. So the idea is we write a test case saying we check to make sure our software is doing what it was supposed to. So say our test case right now is going to be if we run the elevator for 100 seconds, for forever, is it going to go to the right height? This is a question we can ask our software. So what we want to do is write a simulation to simulate our system, and then write our software that goes and tries to do that, and then we can go look at it and see, did it succeed? And so what I want to do is we're going to do that. We're going to then try some air conditions, see if we can break it. And then once we're happy with our test cases, I want to go put it on the real robot, since I brought one. And we're going to show that physics works. So this is going to be interactive. So I'm going to type, but I want you guys to come up with, tell me what to type and what we're going to do. So I'll guide you. Okay, so we're going to start. Wow, that's kind of awkward. We're going to start by, I'll show you what we have here, and then we're going to start writing some software. So this is what's called our test fixture. This has helper functions for our test. So what we want to do is simulate our physics in our test fixture. So the first thing we start with is stall torque, stall current, free speed, free current, and a mass. And then that lets us compute a kV, a resistance, and a kT. So from before. And then dt. There you go. So then the final equation here that's from before is I typed out all of that math and put all the constants in. So what this is giving us is given a voltage here that we're applying to our motor. So right here we have a voltage and the current velocity. What is the acceleration? Does that all make sense? So then I deleted everything else. So we want to write a test. Write a test to operate our elevator. So let's start by so what do we want to put in our function? We're going to simulate our system. We're going to simulate the elevator for a period of time. So given a voltage, it's a good question, given the voltage applied and the time that we're going to wait, we're going to ask the question, where is the system?
Wait, we also need to know where it started.
Okay, good point. So let's make some variables for that. Okay.
Do you want to return the position?
We could, or we can just store it in a variable. There's a bunch of ways to do this. I'm going to pick one. It's going to be slightly arbitrary, and we can change it if it was a bad idea. Okay, so we want to do the trick where we split it up into a bunch of little time slices.
So we're going to want to iterate over time equals 0 to time equals time, and go by a time step each time.
Okay. Let's make a variable. So we'll do 1/10 of a millisecond. Probably overkill. Okay, so now we want to integrate up our system. Phil.
Compute the acceleration at the given voltage.
Okay. Okay, then what? Okay, so how did we do our Euler integration from before? What was the math there? Okay.
So you split it
So
up
the chain, sorry.
You split it up into like a bunch of like small different like bars.
Okay.
So they're basically all rectangles. So the height is the acceleration, and then the width would be the
Our
difference in
time step.
time. So,
Our time step, right?
Yeah.
So here's our little time step. And then the height will be what?
The height would be the acceleration.
Okay, here we go. And then what is that? What does that give us?
So then you can multiply the acceleration by the pace of time to get the area of that one rectangle.
Okay, and then what do we do to that?
You want to sum them all up, so you probably want yeah.
Right? Is that what you were posing?
Yeah.
So we should do the same with the position. Right? Phil.
Why do you have it written in that order?
I think this will underestimate the position. I feel like it's a slightly better default, but as DT strengths, they should converge to the same thing. Because, well, partially this is, we're sampling the velocity and acceleration at the start of the time step by doing it in this order, whereas if we did it in the other order, we'd change it. So they'll both be close enough that we probably wouldn't notice. But, okay. So let me show you. Wow, that wrapped. Okay. So let me describe. Oh, Sean.
Isn't the acceleration given voltage constant? So couldn't you put it outside the loop?
No, it's not. What's this term? So this comes from, if we look over here at our equation, we said the acceleration is some constant times the voltage minus a constant times the velocity. So the velocity is changing, so we want to keep it in the loop, so we're assuming it's changing for less time. Does that make sense? Okay. So let me describe what we need to do, and then we can start digging a little further. So here's our elevator. Let me lift it up. So it goes up and down. We have a Hall effect sensor down here. I don't know if you can see this. So there's a sensor at the bottom and a magnet on the carriage. So as it goes down, the sensor is going to read 0. And then when we get to right above the bottom, it's going to read 1. So when we start this, we don't know where we start because the encoder will read 0 wherever it initializes. So what we want to do is we want to do a homing sequence. We want to lower the elevator very slowly until we see it transition from a 0 to a 1. We want to record that as 0. And then we want to then go to wherever we've been asked to go. Does that make sense? OK. Yeah.
After you bring it down to make it 1 and record that as 0, when it's going back up, does it read as 0 again?
The sensor will always read 0 wherever you turn it on. What we want to do is, here's the interface I'm defining. So this is what the user is going to use to be able to provide to our control loop. So they're going to be required to call update at 100 Hertz with the current encoder, the current sensor value, and a Boolean telling us if it's on or not. And then they're also going to be able to set a goal. So say, I want you to go to a ½ meter. I want you to go to 1 meter. I want you to go to 0 meters. So we should probably be a good citizen, and if they said 10 meters, not drive it through the roof. So we want to put some air checking in here. But this is the interface we're required to provide. Okay? So I think the best place to do, the next thing to do is we should simulate this. We should hook the physics up to this elevator, and then we'll start implementing it. And at some point, we should start running it when we have enough that we think it'll compile. So how do we get encoder here?
What do you mean by how do we get encoder here?
So we need to calculate, maybe I should back up a step. So we want to, say, simulate 10 seconds or a second of operation here. Okay, we want to run our controller on our robot for a second. So let's write that out, and then we'll find a bunch of unknowns and have to sort them out. So we'll use a similar trick here. So then we want to call, we're on an elevator. So how do we get the voltage that the elevator wants? What do we need to call?
What does the voltage depend on?
So, well, what does our interface ask for? The elevators. Oh, did I not document that well enough? There we go. Better comments. So we need to call that method. Okay, now we need arguments for it. What do we pass it? Sean?
The encoder value.
Okay.
Whether the Hall effect sensor senses something or not.
Okay.
And whether or not it should be moving.
Yeah, if the driver station is enabled us. So if the driver station is disabled, the guy who wrote the interface thought it would be useful to have that information in the implementation. So we have to provide it in our simulation. But where do we get these from?
So the encoder, it has to do with your position.
Okay, so what do we type here?
So you would want to, you would want to just start out with position when you haven't moved yet. So, and then eventually, later, you would be simulating time, and then the position would be updated.
Okay. So we want to put what call here?
Position.
Did I spell it right? No. Okay. What next? The first argument, we got 3. How do we simulate our sensor?
I mean, you could just ask if the position is 0, then it should be.
Is it exactly equal 0?
Well, you can have a range.
Okay. So we want a little range. So we're going to say if the elevator is within a small range, the sensor is true. That make sense? Well, the magnet's about yay tall, and the sensor's down here. So I'm going to say it's like 4 centimeters. So let's go put this in a little helper function. So what do we put here, Adam?
Just the position. Position plus, well, sure, you can do that way.
Okay.
Thank you. Other way around, maybe?
Yeah.
Is it?
Oh.
No.
That's negative there. Sorry, go ahead.
It's got to be above the bottom limit and below the top limit. Actually, I should probably erase this now. Does everyone have this? Are we good with this? Okay. There we go. All right, so we got our limit sensor. Sweet. Progress. Oh, shoot, what did I call it? There we go. Okay, what's our third argument? Enabled. What do we want to do there? So what do we start with? Let's just make it true. And then we can, so we're going to start it a little simple, and we're going to get it a little bit wrong, and then we can go make this more complicated. But let's start simple. So we got our voltage. Now we need to simulate it. Simulate times. How do we do that? Okay. Simulate time, it takes a voltage, takes time. Well, so what's time going to be here? What?
Current time.
Well, what did we make it over here? So this is the time to simulate in simulate time. So what do we want to pass in over here?
We can pass it anything.
Our control loop time step. So we want to pass it the tick duration. So our control loop's going to run at 100 hertz. So we want to sleep for 10 milliseconds. So what we're doing here in our little simulation, actually we need to update simulated time. There we go. So we're going to ask the elevator what voltage it wants us to compute, and then we're going to go simulate what happens with that voltage for the time step, and then increment time and repeat over and over and over. Okay? So I'm wondering if we should see if this compiles. See what we're missing? Let's try it. Let's see where we go. Oh, and I got to build the test framework real fast. Oh, there we go. We failed. Oh, look, elevator.cc. There's nothing in it. So let's come up with the simplest implementation we can. Just to see how we're doing. We'll just go and see what happens. And then to fix some compiler warnings.
Is this from Recycle Rush or a different game?
Yes, it is. Hey, test pass. But we didn't really check anything. OK, so we need to now make our test do something useful. So what do we want to actually check? What would be a success here? Well, what do we want to have our robot actually do? Let's go test what we care about. Move to a position, right? So we should probably tell it where we want it to go. So we do that by calling setGoal. Tell it to go to 0.5, and then we want to, how do we verify it got there? Sorry, Neil?
Position.
Okay. Does that work?
No.
Okay, why doesn't it work out?
Well, I mean, what are the chances that it's going to be exactly 0.5?
So here's where we, is it expect near? Let me see if I remember it correctly. A, B, delta, OK? How good's good enough?
0.01.
0.01, so that's 1 centimeter? Seem reasonable?
Or centimeter. It can be the same as the other one, so 4 centimeters.
So the width of the sensor, but we can do better than that. This is asking how accurate can we convert.
But yeah, 0.02.
Well, 0.01 is not bad. That's saying 1 centimeter. I just wanted to get you to think about, when we pick numbers, why? What's the right answer here? OK, well, let's see how we did. No, Oh, undefined reference to set goal. Looks like we got to go write that real fast. So what do we want to do with our goal?
Throw it away.
Sweet. Oh, unused parameter. Let's save it. Okay, and then I need a double goal. No, didn't work. It compiled. We're doing better than we were before. Okay, so, but we made the difference between position and 0.5 is 0.381 something something something, which exceeds 0.01, where the position evaluates to that, half evaluates to half, in case those are expressions. So we actually succeeded in moving. We just completely uncontrolled. So we should probably start, well, actually there's two things we can do from here. One is we could plot it, try and see what actually happened. But we know it's wrong, but we could plot it. And the other is we could try and write a control loop. So how do we control it actually? How do we want to do this? Phil.
Let's plot it.
Okay. So we're going to do the stupidest thing possible, and that's just print it to a CSV file.
You got it right.
Did I get it right?
Yep.
Sweet. Better than expected. Oh, well, actually, question for you guys. What do we want to plot?
Everything.
What is everything, Adam?
Position time, maybe?
Okay, position. Oh, well, so let's start with time. And then position.
Acceleration.
How about goal?
Voltage.
Okay, voltage. You guys are coming up with a bunch of good ideas. What else?
Velocity. Acceleration.
Velocity. I think we should put a header on the file so we can remember what we're plotting. So time, position. What else did we want? I heard acceleration. I want to plot the limit sensor. This is the Hall effect at the bottom that we're going to zero off of, so we know what's happening. Okay. 1, 2, 3, 4, 5. Velocity. Wait, did I count? It's 6 of them, right? Acceleration. Okay. Acceleration. Where did I? Oh, we didn't calculate that. That's in simulate time. You mind if we drop that one? We can add it if it turns to be valuable. Oh, double. Okay. Okay, failed. We have a file. Sweet. Okay. It moved. Okay. So I think we should start. So we got a plot. So this is pretty cool. So we simulated our system doing something, and we went and we plotted what it did, all in software. So that's pretty cool. So what I think we want to do next is we want to try and get it to do something useful rather than just return 1. So let's start. I think we can close the header for now. Let's try and implement this. So how do we want to implement this?
Do a simple thing controller.
Let's do a PD loop, but we need to implement the zeroing logic. So what is the overall structure we want to do?
So you want to go down slowly until the limit is triggered, at which point you zero it.
Yeah, at which point you're zeroed, and then you can do whatever you were going to do normally. So let's write this. Does everyone know what a state machine is? Who doesn't? Okay, that's enough to do it. Okay. So we're going to write out our system. We're going to say our system goes through a set of states. So these states are something like we're going to start with uninitialized. And then let's say running. And then I always like to put an e-stopped state. So if something goes horribly wrong, you go there. OK. So we're going to start uninitialized. And then at some point, we're going to move to the zeroing state. And we could potentially come back if we wanted. And then when we're done zeroing, we want to move to the running state. And then eventually, I guess we could say running could e-stop itself if it gets really unhappy. So now we need to ask the question, so when do we transition from, so we can have different behaviors in these different states. So running, we're going to go to wherever you asked. Zeroing, we're going to move down slowly, trying to find our sensor. Uninitialized, we're just going to wait until we've done whatever we need to do to initialize, save some variables, maybe wait till it's enabled. And then e-stopped will be if we're upset. So here, when do we want to transition from 0 to running? OK, great. OK. And then I was saying we could transition here when we're enabled and disabled. We'll see if this is a good idea when we go write it. OK, and this one is on error. OK, so now let's go try and implement these various states.
Hey, Austin.
Yeah, Phil.
I don't know if it's worth talking about, but just to clarify maybe what the difference is between the reading that the encoder gives you versus what you treat to be 0, like after zeroing versus before zeroing.
Let's come back to that.
Okay, fair enough.
We could be a little too simplistic, and then we'll go break our model.
Sounds
and then
good.
we'll fix it.
Cool.
So I'm fine with being slightly wrong, just not before we put it on the real hardware, because I don't want to break it. Fred.
Do you want any other exit from the running state than error?
Not really.
Okay.
You don't really need it.
You don't really need it. That's why I asked it as a question.
OK, so we want to code up a state machine. I'm going to close the test case until we actually have something more to do. Yes. OK, so we need to write a state machine. How do we code this up? Oh, just
You have like a switch statement where you have all the states. Define a variable called state.
let me get typing.
Another question.
Oh,
Or,
sorry, I can't type in.
I was just going to suggest a state even.
Yeah, I was starting to.
There.
We'll use C++ 11.
Perhaps not going to be practicing.
Yeah, well. OK. Okay. Now what?
Case case.
Oh, shoot. Good call. It still doesn't do anything, though, when we fix that. Should we start adding our lines? Sean?
In state uninitialized, if the robot is enabled, switch to state zeroing.
Okay. Okay. What next? Sean?
If limit triggered in state zeroing. Set position to 0 and set state to running.
Okay. How do we set position to 0?
It's simple variable assignment.
I can set encoder to 0?
Do you have a function to 0 the encoder?
Nope.
Have a variable for encoder offset.
There we go.
Equals encoder.
Okay, so then we can probably then calculate our position. I'll do it up here.
Actually, you may want to put the if limit triggered in all of this in state running as well.
Why?
Just so to avoid glitches.
I will argue that's a bad idea.
Why?
If we're moving really fast, there's going to be delay, so there's going to be more uncertainty. So we can move really slow and get a really good edge, and then we'll be more accurate. So something we could do, if we wanted later, when we have something working, is we could look at the edge as we move by and see if it looks reasonable, and use that to throw us into the e-stop state. So say the chain slipped, and we zeroed it at like 2 inches off, 10 centimeters off later, and we got a different edge. I would argue that's an error, and we should probably shut the system down. Does that make sense?
Okay.
Okay. So, let's encoder. Is it encoder? How do we compute the absolute position now that we have our offset? Okay. I'm going to flip the sign to help my brain, because I always work with it the other direction, but it's all the same, mathematically. Okay, so now, actually we should probably update position now to be, okay. So we got to implement our behavior where we start moving down slowly.
And in limit triggered set state running.
I did.
Oh, it's that.
I was doing that while you were thinking.
If you really want to capture your state machine, you've got to also in there say if not enabled, then state initialized.
Okay. Good?
Do you really need to re-zero every time you're enabled?
No. Once we're running, we're good.
Then why do you set back to state uninitialized? From state
I
zero?
will argue that we're going to find some logic we really want to put in this if statement on the edge. So that's why I made a distinction. So we need to, how do I want to do this? So the way I like to structure control loops like this, let me give you a little more background, and then we'll go implement it. So I like to set things up in terms of chains. Okay. So the first thing we're going to do is the user is going to pass in a goal. He's going to say, I want you to go to half height. So then the next thing we want to do is we have our state machine here that's trying to decide if we are ready to obey the user or if we need to zero. And then its job is to generate a goal. Maybe goal prime. This is a modified goal. And then we want to pass this goal to, there's two ways we can do it from here. We can pass it to a profile, and then to our controller. And this is a voltage. So this would be, say we want to limit the velocity that we move. We could say, hey, we were asked to go to minus 10 meters or plus 10 meters. We're only allowed to move 1 centimeter every cycle. So just move it a little bit at a time. We can do more complicated profiles here. And then the control loop says, I now know where to go for the next cycle. What voltage do I need to apply to do that? So you can do it that way, or we could bypass the profile. You get a choice there. But for our action where we want to slowly go down until we find the edge, we need to have something needs to move slowly. Move the goal that we pass the loop slowly. Yes, Sean?
I would put the profiler after the controller rather than before. So that if you want to go up to plus 10 meters, you can actually slow the voltage down instead of going bit by bit.
The profilers, well, you move this at the same rate that the controller updates, and so it's not bit by bit. It's actually continuous. So every cycle you move at the same increment. What you want to do is essentially you want to compute a trajectory. I want you to move this way, accelerate with this power, do all that. And then you tell the controller, this is how I want you to move. And then it solves the equations of motion to figure out what voltage to apply.
Oh.
So that's a higher level view. We're going to do this really simply. We're not going to do any feed forwards because we don't need it. And we're just going to use a PD loop, not some complicated math. But all the concepts still apply. So let's go start to implement this. Okay. So how do we want to move down slowly? Actually, should we do move slowly or do the controller first? A controller. I heard a controller vote. Okay. Hang on, it's a good question. KP, it's a constant proportionality. We need to define it. If we get it wrong, it's going to go unstable. But we have a simulation, so we can just go try it and see how well we did. It's the beauty. We don't have to break the robot the first time we run this code. It's really nice. So let's...
What's the constant?
We'll pick 1.0 for now. So let me finish writing this out. I have no clue if that's the right set of constants. We get to go test this. So what we're doing, let me scroll down a little further. So we're taking our air. This is the difference between where we want to be and where we are. And we're multiplying that by a constant. So we're just applying a voltage proportional to the air. So we can actually go back to the motor equations and we can show some cool stuff here. So we have V equals IR plus omega over KV. So assuming we're at the same speed, if I change V, I add a volt to V, but I haven't sped up, what happens to the current? It increases, right? So it increases proportional if this is fixed, it's going to increase proportional to the resistance. So delta V over R equals delta I. We know KT times I equals tau. This is our other part of the motor equation. So if we do delta I times KT equals delta torque. So by changing the force, or changing the voltage by a delta, we get a change in torque, assuming it doesn't accelerate. So the cool thing here is our air is now, this is a function of the distance away we are from where we want to be. And we're computing a voltage that's proportional to that. So we're getting a force that's proportional to our air. What physical thing looks like that? Where you get a force that's proportional to the deflection? A spring. So we have a software spring. That's all it is. Yeah, Phil?
On line 41 there, is that goal minus last error? Is that?
Oh, did I mung that up? Yep. Good catch. We're going to catch that in testing. Good call. So then the other one is kV is another constant, and we multiply that by the velocity, or the velocity of the air, how fast the air is changing. So this is probably something you haven't run into, but something where the force is proportional to the velocity is a dashpot or a damper. So we're gonna pulling energy out. It's like moving your hand through water, that type of system. KDT? That is the time constant. Time step. The amount of time that elapses every time we get called. Okay. So we got a little control loop. I think it goes to 0. No, it goes to goal. So we need to start adding our profiling in. So how do we do that?
Can we ignore it for right now?
And see what happens? Sure. Nope, not yet. We have a number of errors saved up for us. Line 13. Oh, I didn't save. Let's try that. Much better. Oh. This is a live demo. Okay. Huh. Something happened. Is that what we intended? So let's try and figure out what happened. What else should we try and plot to figure out what's going on? Okay, voltage, what else? Okay, which one's which? So voltage is the third one. Geez, we asked for 50 volts. Is that possible?
No.
Okay, so we probably shouldn't do that. So what do we want to do about that? Well, actually, first thing with test-driven development, if we ask for 50 volts and we shouldn't have, what should we do?
Figure out why.
That's the second thing.
Make a test that fails because.
Yes, we should have our test fail because we did something bad. We found something we should have failed on, so let's go fail, and then we should go fix it. So we gotta go fail.
For all the voltage readings, make sure they're within the range of 12 volts.
Okay, where should we do that?
In the test program.
Yes. Where?
after generating all the output, go through and make sure there aren't any. Actually,
Well, on which
all the
function?
tests
I'm asking for
immediately.
which line. I'm asking a lower level question.
Insert a line after line 85,
Okay.
and make sure the voltage isn't above. And expect it to be greater than -12.
Okay.
That should do it.
Okay. If we want to create a second test case, and then we want to copy this, so where would we want to move it? How about we put it in simulate time?
That's probably better.
Sweet. Okay. Let's see if our test fails. Sweet. Okay, we should fix this now. How do we fix it, Sean?
That's what I'm trying to figure out.
Then what do we plot?
Error and just error and goal.
You're gonna stress me. Okay. So error and goal.
Yeah.
Okay, goal. Let's expose that.
Couldn't you just plot last error because you're assigning last error and error the same value?
Yeah. Let's do that. We want a goal and error.
Isn't the problem the first time you use last error, you never initialized it?
Is that it? We initialized it to 0.
Where?
We're using a C++ 11 initializer.
Okay, never mind.
Okay. Okay. Do you remember which index, Sean, or should we count it? 1, 2, 3, 4, 5, 6, 7. Okay. So we're being asked to go here. What is that number?
Don't see much happening.
We're zoomed way in. 0.48. Is it 0.5? Oh, we're being asked to go to 0.5. Okay. So then our error, this 50 points really throwing the plot off. Did I not plot the error? I may not have. Oh. Skipping data file with no valid points. Okay. 1, 2, 3, 4, 5, 6, 7. 7 and 6.
Why is nothing happening, and why is it initially trying to run the motor backwards?
That's a good question. So probably what happened, what I'm going to guess is happening is we're computing a large velocity change because the air is changing quickly. So one of the answers here is let's just cap it. Just don't let it through. Which is going to be the right answer here because our control loop doesn't have a concept of saturation. So all we really can do is cap it. Well, so let's do that.
But you said test to fail
Yep.
when it was greater than 12 or less than negative 12.
Mhm.
So why are you capping it?
I'm capping it in the control loop. I'm not capping it in the simulation. It is not reasonable to ever ask for something outside of that range.
Yes, so why not with the program if it's outside of that range?
I would argue we can come up with a reasonable case during the runtime that would crash the program in that case. If you change the goal quickly, we're going to get a large, what's going to happen is error minus last error will be large.
Well, then set last error to 0 when you change the goal.
What if the robot's moving quickly? Or we have a large proportional error. So KP is driving it out of range.
So the basic idea is you're telling your simulation that you want it to respond to a particular set of stimulus. Well, making a set of stimulus that doesn't really make sense. So it may come up with a next step that also doesn't really make sense. It may say, oh, well, to get there quickly, I should use 50 volts. And it can't use 50 volts. So that doesn't mean the simulation is wrong. It just means that the input to the simulation doesn't necessarily make sense. So we can leave the simulation alone and we can look at the part that we're going to use from that simulation and force it to make sense. And that's the capping that Austin's talking about.
And we can do more complicated stuff in the future. Just this is definitely the simplest way. And this is now physical. We're not asking for something that we cannot achieve on the real hardware. So we've made our simulation more realistic. And that's a good thing. Oh, so let's try it. I'm using a variable here because when we do bring up, I don't want to turn it all the way on the first time. So we're going to turn everything down. So I'm being a little prepared. Oh, I love you too. Still failed, but we can.
That's fast.
Hey, okay, that's better.
I don't see what changed.
Well, the max went from 50 to
Just
5.
max went to 5. So
But I was
Sorry, what?
expecting it to go to 12.
Yeah,
did he?
it's the max cost.
So algebraically, if we work this out, when we start up, I'm just going to give you the answer rather than, we could debug it and dig down deeper, but we don't really have enough time to do that. So last error starts at 0, goal is 0.5, and position is 0. Okay, so error is 0.5. So 0.5 minus 0 divided by 1 over 100 is going to be 0.5 times 100, which is 50. So progress. I kind of want to let it run longer, see what happens. Should we try it? Okay, we're going to do it. See if it's actually stable, or if it just, because it hasn't stopped yet. It keeps moving. So I'm kind of curious. Go 10 seconds. Is that stable? Voltage.
I don't really see that much action.
I'll go longer. Did you change? It's actually stable.
Just write it for longer.
It's 100 seconds now.
Okay.
Which I will argue is not something that we can put on the real robot. That's going to take too long. We can't take a match to move the elevator. But we did simulate a control loop. The control loop is stable. I would have sworn we would have had a negative sign somewhere, but. Come on. Yeah. Cool, so we're converging. Okay.
So, sorry, I'm not saying the plot very well. How long did it take to convert?
It's about it's a time constant of like 14 seconds. So we get to 60% within 10 seconds or so. Which is, this can go faster.
Yeah, from that perspective, not a good number.
Yeah, but it was stable. Okay, so we can tune the loop a little bit, or we still haven't implemented our zeroing behavior.
Run when in state zeroing, set velocity to negative 0.5.
Okay, how do I do that? Our loop right now just takes a goal, which we can move up.
When in state zeroing, set the goal to negative 0.5. Is it not position?
It's a position goal.
Position goal to 0. But the
we can try that. Sorry.
That'll do.
Sorry. Where?
Oh, where are you setting
This?
velocity to negative?
So let's define our coordinate system. So how do we measure the position of the carriage? What's 0 and what's positive? We have to agree on a coordinate system. It can be arbitrary, but we all have to talk about the same coordinate system or we won't be able to put the elevator in the same spot.
Positive velocity is up, negative velocity is down, 0 is staying still.
Yep, so we're going to say 0 is when the sensor just triggers, for why not? And then positive is up. So to go down to this, to go to the sensor, what direction do we need to go?
Negative.
There you go. That's why we're going negative. So you want to say goal equals 0 here, Sean?
Is the encoder initially set to 0?
Yep.
Then set goal to negative 1.
Okay.
And have the test software trip the limit switch when it says that it's set to 0. And have it start at a random position too. That'll fine.
Okay. Let's do these one step at a time. Yeah, we're going to do it in this order. Actually passed. Okay, so let's see if we can decode what actually happened here. So goal is blue. Well, so that's the goal we were past. That's not the goal the control loop executed. So maybe we should plot that. Yeah. So this blue goal, if we come over here, the screen's getting a little too cramped. This is elevator.goal. Right here. Elevator.goal. So if we trace that, that is goal here, which is goal underscore, which is from set goal, which is called here. And then if we go look here, the goal that the control loop's exercising is this goal, which is assigned there and then modified there. So we're not plotting this one. So let's plot it.
Alright, just assign goal.
Because then we will have thrown out the user's input. We don't know where to go after we've zeroed.
Oh, got it. What is filtered position?
Sorry, did I call it filtered goal?
Yes, you called it filtered goal.
Yep. Thanks, Sean. Okay.
Also, in a test program, I would have it just, you know, for the sake of it being a test program, have it start with the encoder a random number, and have the position 0 be at a random number.
Okay, so let's upgrade our test. Now that we have something that pretends to pass, let's try and make it more complicated. Okay. So right now we're starting at 0. So how do we update our test to break that assumption?
Where is it assigned 0?
I'm going to have you answer that question. It's on the screen. I can't keep it on. So where have we made the assumption that the encoder starts at 0? Absolute. What do you guys?
When you set position on 0, it's not on the screen, up further.
Okay, so this is our initial position. So we could change that.
Set that to a random value each time the test is run.
Let's pick a set of values that we think are interesting, rather than random. And the reason for that, just a little bit of background, is we want reproducible test cases, so that when it fails in the fields, you know, I get a bug report from someone, they come and say, hey, I ran your test and they failed. I don't have to guess what random number they picked. I know what numbers they picked. So if we want to pick a random number, we want to pick a pseudo-random number that follows a specific sequence, so we can debug it.
have a random encoder offset too.
Okay, so that's another thing. So why do we want the encoder offset? What will that give us physically? So when we boot the robot like this, what's the encoder going to read?
0.
Okay, and what's the actual position? There you go. So it's going to be, the offset is going to be the starting position, essentially. So we can break that here. I'm going to pull this in a function. Okay. Okay, so now we have more complicated tests. Okay, let's go look at it. That looks way over damped. Yeah, this is rather interesting.
glad we didn't do that on the robot.
Me too. This is why we're
looking
going to position, voltage, goal, and error at the start for what you had suggested.
So what are you concerned about in this graph?
This doesn't look controlled to me. I don't know.
So you suddenly jump from negative voltage to positive instantaneously.
Yep.
What's wrong with that? That's exactly what I expected it to do. It's zeroing out, and then when it reaches 0.
So the other thing, there's some knobs we need to add. Just trying to figure out how to motivate. So we want to make our motion down be more controlled. Right now we're just telling it to move a meter down from where we started. It might go full speed. Which...
It looks to me like you're not passing in much voltage.
Our control loop isn't very aggressive. Right? It takes 10 seconds to converge. So we can tune that up. We'll see some more interesting behavior. So let's do that.
Yeah, make it like...
Negative voltage? It means you hook the motor backwards to the battery. That's electrically what it means. That were negative? Because it wanted to move down to find the sensor, right? So we started here at 10 centimeters, and then we tried to drive it down until we found the sensor, and then we allowed it to go up. So to go down, we need to apply negative voltage. So practically speaking, that makes sense. KP, 10. Don't do things halfway. It's probably still not enough. You getting somewhere?
Voltage.
Yeah, starting to get somewhere.
Oh.
Still too slow. Oh, good. We can stop simulating 100 seconds, though. Like 10's good. But really, this thing it moves faster than that, so we should be able to converge a little faster. Okay, there's still multi-seconds to converge. Do you see how I'm seeing that here? What does that mean to you guys? Why do you think why am I saying that from this plot? It takes a long time to get it to come down, right? So we can look at this exponential, and we can pick somewhere around here, like 60% done or 90%, or we can pick some metric, and it's taking a number of seconds to do that. So we should go faster.
Decrease KD. Maybe. Not to 0.
Nope.
Nothing happened?
Not much. Oh. Need more KP?
That's a lot of KP.
So let's give this thing physical units. What are the units on KP?
There are none.
You're incorrect. There are units. Proportionality. So what is KP is it has volts on the output, and it has an error on the input, and the error is in meters. So it's volts per meter. So we have 100 volts per meter.
That's a bit much.
Is it? So that says that at is it like 8 centimeters, we're going to apply full voltage. That's actually kind of okay. So we're looking locally.
If you try to go from the top to the bottom, it's going to apply to 100 volts.
Yes, and then it's going to be saturated to 12, hold 12 until we start getting close, and then ramp it down.
Oh.
Which is that's what we wrote, and that's the behavior we want.
That makes sense.
So let's try it. That's getting somewhere. It's starting to get somewhere. Okay, let's go look at the time constants on this and see if it's what we want. Let me see if I actually want to run this on the robot. Okay, so we're at a time constant of, what are we, from there to there? So about 0.12 seconds, somewhere there.
What about the zeroing period?
That's one.
here. So we are zeroing with whatever we capped it to, full, the whole time.
That may be bad.
Okay, well.
I don't really think you want to. I don't think you want to floor it going down.
Nope.
Because it's going to hit the bottom with some force.
Okay, so if it's going to hit the bottom with force, what should our test case do with this current code? Fail. Okay, so let's make our test fail.
Yeah, so check the velocity when the limit switch is higher and see if it's like pretty high.
I like that idea. So how would we write that?
So you can see like, yeah, like if the limit switch is triggered, and you can see, you can do like a similar thing with expect that it's like less than, I don't know. That's like here, that was.
How fast? What's a reasonable speed to be zeroing at? Let's just make one up.
I don't know.
Pick one.
Sure, I don't know. Sure, 2 meters per second. I don't know.
2 meters a second?
No, that's bad. That's bad.
This top's on the bottom.
I don't know.
Move your hand at a speed that you think would be safe.
Like,
I can't see your hand.
like that.
Let's go a little slower.
Or like that.
So about how fast would that be in meters a second?
So,
Less than that.
point oh, yeah, 0.05.
Sounds good?
Also, when you are going up, you're going to be going faster than 0.05 meters per second.
This is if limit triggered.
Yes. The limit is going to be triggered when you're starting to go up.
When you're starting to go up, you will be moving slowly
Why?
as you're reversing directions. Because it takes time to accelerate. I think this will actually pass.
Let's try it.
Yeah. Well, it failed. So it failed because it's supposed to fail because we knew we were being too aggressive down when we're zeroing. So that's good. So we need to fix that. So we initially started zeroing at minus 0.6 meters per second is how fast we got across that limit. So we need to update our control strategy to be a little slower. So what's a easy way to do that here?
Gain schedule, or going down versus going up.
That
KP and KP.
you can, but you're better off using that to compensate for gravity and friction, which is not our problem here. Our problem here is we're telling it to go a meter and letting it rip.
Increment the goal based on the position.
Okay, we'll go with that. So how do we? It's an easy way to do that here.
Just set your goal equal to a small increment less than your current position, and just put that.
I have a constant for this. Yes. K zeroing velocity. I think that might work.
Well, your
Take it.
zeroing velocity currently 0.
Sorry, what?
No, 0.01.
Oh, it's
0.01.
Multiply by dt.
Yeah.
Why are you decrementing the goal?
So that we don't go too fast while we're zeroing.
Can you start?
So I start the goal
Why
at the current.
not special case state zeroing in your control?
The architecture of our loop says that we don't want to do that. We want to keep our loop the same for all of this, and that makes as the control loop gets more and more complicated, as we make it more difficult, we want to preserve that.
I would just say, do what you're doing there, only in state running, and anything else you add to the control loop, do it only in state running. And in state zeroing, all you want to be doing is going down at a predetermined velocity.
But the loop that we had before did not control the velocity. It just gave it a position of -1 and let it rip, which is not controlled. So we need to add the concept of a velocity to our loop. And the easiest way to do that is to move the position slowly over time. So that's what we're doing here. We start it at when we enable, we capture the current position and say that's where we should be. And then every time step, we just move the position down a little bit each time. So that implements our simple little profile box over there, which we then feed into the control loop.
Couldn't you just have the control loop say, if I'm in state zeroing, give the motor minus 0.5 volts until I'm not in state zeroing anymore?
That won't break friction.
Minus 0.5 of maximum,
That's going to
minus 2 volts or something small like that.
It's too easy to get that stuck. We want to move at a slow velocity. That, if we get any disturbance, it's not going to ramp the power up.
Oh.
So really, we want to let our control loop, because we have a piece of code here that's really good at moving things to positions. We want to have it do the motions. And we want to keep it simple so we can analyze it mathematically.
Okay.
We're going to assume so. We can break that assumption later if we want. Did we just not get there in time? That's entirely possible here. No, did we go up? Did I do that? No, going down.
What did it do?
That's our what we need to figure out. Goal.
Never went down.
Wait.
It never went down. Okay.
When did it change the goal?
You didn't give it a goal to go negative.
This should move it down though.
You didn't give. You gave it the original. Where did you give it to be a?
Oh,
When
you're right.
you start to zero, you
Negative
don't know
goal.
what position you're at.
There we go. Yeah.
That's the point of zeroing.
Yeah, that's why we grab the current position. We're relatively off. We don't know where we are, but we're going to start there and move down.
I assumed that if you were in state uninitialized or in state zeroing, position was a garbage value.
It is then relative to where you started.
When you turn it on, the sensor's going to say it's at 0, but the encoder is not at 0, or not there. Sorry, the Hall effect is saying you're not at 0, but you got to give the robot something to go on from there. So you just start at 0 and slowly move down, or you slowly move negative until you the Hall effect says you're at 0. Once the Hall effect says it's 0, you update your position and say this is true 0.
In this case, you want to move the position because you want to go like a certain amount down from where you are currently in position to that value, so it's not relevant to the whole.
It's not useful. So awesome.
Oh, so when we run it with the overriding of, we get to here, so we're moving down. This looks like a controlled motion down. I think we just didn't wait long enough.
Multiply KDT times K zeroing velocity by 2 or change K zeroing velocity.
Yeah, let's do that. We'll go back to your 5 centimeters a second. Hey, progress. So what did we do? Position. So we went to point 1. Is that correct? So why did we do that? Anyone have any ideas? Oh. I think here we are. You need to speak up a little more.
Are you counting for encoder offset?
We are in the position. Well, so without this line, which wasn't there, we would use the previous goal from zeroing, which is, yeah. I think this will fix it. Sweet. Okay. That looks like it's getting somewhere. It looks like it's getting to our goal. So our test is still failing, so we need to figure out what that's all about.
On the plot that you just showed, why did the error points greater?
Here? Yeah. So this is when, so let's go look at the goal. Because the error is going to be driven off the goal. So what's the goal doing here? So here we're starting at where we turned it on. We're slowly moving down. And then when we've finally zeroed, we're giving the goal over to whatever the user asked for. So it goes straight to whatever they asked for. So we stop modifying it. So at that point in time, we're going to have a jump. We're going to have a discontinuity. Okay. So making progress here. So our test failed still. So we should figure out what happened.
Looks like we're just going too fast.
Okay. How do we want our? So there's two questions here. Do we want to fix our system, or do we want to fix our test?
Is our test wrong? What's wrong with our test? I mean, is there a problem?
So what is it? What are we measuring here? What's this test checking?
How fast, whether our velocity exceeds 0.05 meters per second.
Plus or minus, right?
Yeah.
Do we care how fast we go up? Maybe we can just say, don't go down fast.
That's what I was saying earlier.
All right, test pass. I'm getting somewhere. So I want to, let's see. So I think we have a half an hour left. Is that it? I want to put this on a robot, but we also need to make sure that we're comfortable with it before we set it live. I don't want to break it. So let's poke at it a little more. So what are some other things that we want to test? Things that could go wrong?
Hit the top. Don't want to hit the top.
Okay, so if the user asks for 10 meters, let's see what happens. Oh, we got close. So we can wait a little longer. Come on.
There you go. It's 5 minutes.
Well, so we just haven't converged yet, it looks like. Well, let's... Oh. Okay, test pass. Should they pass?
No.
Okay, so let's go fix our test. So where do we want to test this? So you guys are quiet over there. Someone over there. Where do we put all our other tests? All our other check statements, assertions?
Test.
In the test, sure. So where in the test?
If you just put it in either where you simulate or by your controller.
Okay, let's put it in simulate. That sounds good. What do we want to test?
Just make sure that the input doesn't exceed the height or go below the height.
Input. So what is that?
Or
how do I write that?
The goal. If the goal is higher than 10 or higher than 2.
Okay. From our test's point of view, though, what do we actually care about? physically here?
Or the position.
Okay. Yeah, we just don't want to drive it outside of range. Who cares how the control loop does it? The physical limitation here is I never want to see it go above, say, 1 meter and below 0. I think I gave a constant for that, so I can tune it. Yep. Max height and min height. Okay. Oh, good, it fails. Progress. Okay, so now we should fix this, right? Make our test pass again. So what do we want to, how do we want to write that? What do we want to do if someone asks for a goal out of range?
Just set it to the maximum height.
Okay. We'll do it over here. Oh, algorithm. Okay, so what happened? Small fraction of a millimeter past the limit. So mechanically, so what do we want to fix, the test or the code? Okay, we want to fix the test. So we should probably just let it go a little lower. We could go measure it or say it's probably about 1 centimeter. So we'll give ourselves a little bit of a margin here. So the way I like to do this conceptually in our code, we'll be a little sloppier here, is have a hard stop and a soft stop. So the hard stop is when you hit the physical limit, and the soft stop is the max and min that the control loop will ever let you go. And so you generally keep one slightly inside the other. And then your test case tests for the hard stop, and your software constrains you to the soft stop. So rather than make those explicit, I'll hard code the number here. But that's a concept I like using for this. Okay, test pass. Doing better. We've made some progress. Okay, what else can go wrong?
The Hall effect could be broken.
Okay. Well, I'd say good point. I'm not sure we have time to simulate that here. So there's another thing that I want to check here that I like to do. It's not as obvious, is I don't want a 0 with 12 volts. If we don't know where we are, let's keep the voltage down, and then when we're ready, we should be able to crank it up. Okay, so we want different limits for zeroing and full. So do I already have max voltage? Okay, I think that'll do it. We should probably write a test for this. Where were we? Here we go. So we need to conditionally check the state. We need to change our limit based on if we're zeroing or not. So what's a good way to do that? Oh, what did I do? State. Oh, do we not expose it? Oh, okay. Okay, doing better. What else can we think to test?
Start the arm at some insane number, like anywhere from 5 to 10 meters up, and make sure it doesn't slam on the way down.
Well, so if we start it up high, what's going to happen? Up really high. What's our test fixture going to do? It's going to throw an error because you're out of range.
Oh, then start it
There's
as
a
the
feature.
maximum, too.
Sure. Well, so I want to split out. I got a little sloppy. Let's clean this up slightly. So let's have our first one, which is if it zeroes in range. Okay, and then we want to ask for a really high goal, except 20 minutes. Okay, I need to type faster. Thank you, Fred. Well, so we'll split this up into 2 test cases. So we'll start out with the zeroing case. We're going to ask for a reasonable value. We're going to use everything nicely. And then we're going to have the insane value where somebody asks for 10. Make sure that works. So some other tests we could add is we could ask for, go below the limit, ask to go to -10 and see what happens. Make sure our loop responds well there. You had a really good idea. We could fail the sensor. That would be pretty easy to do in our simulation. I feel really comfortable making that change and that we wouldn't break the hardware. Whereas on the real robot, I be a lot more hesitant. So yeah, I think those are good suggestions. I think we need to go put this on a robot now. So let's look at that. So I have a bunch of code already written for us that boils down to, we have an iterate loop method, which we can show you. So that every 10 milliseconds, we sleep until the 10 millisecond period has finished, and then we iterate. Just repeat over and over. An iterate loop, we pass it the encoder, we pass it the sensor, and then we tell it if we're enabled. And then we take the result of that and we feed it to the talons. And then here, we're going to have to figure out which buttons, because I don't remember which ones are which. Then we change the goal based on what button's been pressed on the driver station. Okay? So if we've done our homework right, this should work. So the first thing I want to do is I want to verify the sensors, because the robot got unplugged when it moved here. So we'll do that real fast. Oh, there we go. Okay. Ah, good. Negative and negative. That's good. Okay. So the first thing I'm going to walk you through how we bring robots up. We bring them up very methodically. So the first thing we do is make sure all the sensors work. The next thing we want to do is make sure the motors go in the direction we think they go. Because we made some assumptions in our controls that positive power drove the rotor up. So for grins, you can see I've done this before. Let's just apply that much power and make sure everything goes in the right direction. Okay, so if this works, it should just slowly drive down. Let's start it up. Okay. That's good. Okay. We're doing better there. So when we turn this thing on the first time, are there any other precautions we want to take? Anyone? Do we want to give it 12 volts the first time? Okay, so let's go turn this all down. So zeroing voltage, max zeroing voltage is 4. That seems pretty safe. So let's make this one 4 as well. Okay. Actually, and then the next question, which I did not prepare for, is we got to find 2 buttons. 4, 40. Okay. That should work. Okay, so we turn the power down. I think we're good. Let's try it. Okay. worked. So now, well, I want to turn it up. Ready? There we go. Nice. So that went really well for bring up. Like, we changed nothing, and it just worked. So, I mean, that's the power of having a good model. And up until the last 10 minutes, we didn't need a robot. So this is how we bring up all of our robots on 971. Generally, they get done week 6, and we need to start programming week 3. So we have 3 weeks where the hardware does not exist, where we need to do all this. So we develop models, then we write tests, and we simulate it. And then when the hardware shows up, we go and verify that the hardware behaves how we thought it would behave. We check all our sensors, we make sure the motors are plugged in right. Then we turn all the voltages down, and then we try and control it and see what happens. Yeah. Any questions? Fred.
Could you walk through how you're flipping back and forth between compiling for your simulation and compiling for the RoboRio?
Sure. So what we've got here, so we are running...
Using the same source, right?
Yeah, same source. So we're using Bazel as our build system. So I've got it configured to do a bunch of things really nicely. So here's our library. This is a library for the elevator. So we have a CC and a header. And then here is our test case. So it uses the CC code, depends on that library, and our test fixture. Okay. And then our binary uses this, depends on that library, and then pulls in WPI lib, some of our other code, some initialization. So those are our targets. And then the two things I'm doing is we can go up. Where is it? Yeah, they're fitting both on the screen at the same time. So here we're running our test case with the optimized mode, and we're picking the default architecture, which is K8 or AMD 64. And then here, I'm specifying the CPU to be the RoboRio.
That's basically it.
That's it.
Wow, cool.
So this took a lot of work to get set up, but now that it's set up, it's really easy. So some other things we can do.
And the Bazel environment, is that something that you share out and you pull down from the 971 webpage?
So this is actually put out by Google. This is their internal build system. Works for big code bases. So some other fun things to answer part of your question is we can do. Just go run all our tests in the control loops. It'll take a moment to compile it, but yeah, maybe more than a moment. But we have about 100 test cases, I want to say, across all the robots from the different years, where we can go run all the little simulations. And our simulations are only slightly more complicated than what we wrote together. We do a slightly better job solving the differential equation, because it's the same every year. But mostly it's about the same. The simulation side's easier than writing the code. Steve.
Any suggestions on how teams might build up? They're starting at a low level, how they might kind of tackle this in pieces?
Yeah, so I painted a picture of how you can do the overall system. You can start with smaller functions. So it's a little bit of a contrite example, but say we wanted to write a min function. We could go write a test for the min function and make sure that our little function works and not test the whole overall robot. And we can start with smaller pieces of our system and test those and then build out to eventually testing the whole thing. So if you can start to figure out how to build some sort of testing into your development, then you'll be a lot more comfortable making changes because you'll know if you broke something. And you can slowly grow out to bigger tests. It's a bit of code, Fred. Yeah. Yeah, in the back.
What's AOS?
So we wrote a lot of infrastructure for our robots. We have a message passing system that we use, so we can send messages between processes, and that's that library.
And then all this is based on or predicated on controlling one motor. But many of your robots have more than one motor. So how do you test the interactions of the motor controllers?
For most of our systems, they're actually independent. For 70% of our systems, they're independently modeled, and so you just have a bunch of different little simulations. And if you have a coupled system, then you got to go work through the physics to sort out what the behavior is, and then you get to simulate it that way. And then we feed where we call our update function with our...
So your shooter arm, that had multiple...
Yep.
That had multiple motors on it, though.
Yes.
So you independently ran tests on those, but you never knew that they worked together until you put on the robot.
2016, right?
Yeah, I don't know. But you never knew if they worked together until you went to the robot.
I was just going to show you.
Oh, okay.
I have all our code. It's not a secret. It's all open source if you want, and we're happy to answer questions. Should we start with the test or the code? I'll start with the test. I like tests. So where's a good spot? Oh. So here's our simulate method. Simulates a single time step. We do some tricks with some matrix math to reorganize the controls so you can solve them generically. So you can rewrite your differential equation. The intake is pretty simple. It's a matrix. It's a single dimensional matrix. So we're just passing the input in. For our arm, we modeled it coupled. So it's a 2 by 1 matrix. And then, yeah. So how we were checking if we're zeroing, we have different voltage limits. Here's where we're checking the same thing in our test fixture. So if we're zeroing our 2016 arm, I really don't want 12 volts applied. If we're not, or actually landing. So if we're getting close to the bottom, we don't want negative 12 applied. So we had some checks there. Let me know if I'm going too fast. X, so this is our model. X is the state vector, so position velocity. So we're making sure that it doesn't go outside of range. We're simulating it for one single control loop tick with a U, checking various quantities. Here's where we're simulating the arm. We're passing in the matrix. Didn't fully answer your question.
No, I'm a newbie at this, so I don't...
Okay.
The question is, how much more complex does it make the model when you're trying to... So, for example, this guy here, is it one motor or two? That makes the elevator go up and down.
This one is one. Oh, well, it's 2 motors, but they're together.
Yeah, because they increase torque.
Yeah, so we can either model that as a supermotor with a kV and a KT, or we could take KT and multiply it by 2, or the torque out of the motor and multiply it by 2. So we can work the physics through for this to make that work. And since I actually have this robot, let's close that. I mean, here's where we worked the physics out for it.
But if you were trying to model to coordinate multiple motors, say you were trying to lift it with 2 separate motors controlling left and right lifters.
Yes, that is this model right here. Let me find. Yeah, this one's a little more awkward. It's hard to get it all on the screen. So we just generate larger matrices. So you can rewrite, this is going to be harder for most people to follow. We can rewrite our second order differential equation as a bunch of coupled first order differential equations. We have x dot. This is a matrix. We can rewrite it in this form. and then you can solve it with linear algebra. And that's what we're doing here.
So if you think about it in terms of the runtime, let's say you've got an articulated arm. It's got 2 motors, right?
Yep.
So you're solving all of this. Is the time step the same for all the motors? Because my next question is going to be, it seems like all you guys, seems like what goes on a lot is you sit there and you poll your sensors, right? And then you figure out, oh, okay, now I'm going to set up whatever my trajectory is, right? You apply that voltage, and then you go to sleep until the next time.
Yep.
So if everybody's running off of the same timestamp, for instance, then you got a whole bunch of processes that wake up at times, right? And you haven't shown how, or maybe there isn't, you don't seem to be worried about the fact that one of the articulated motors will be turned on first before the other one was.
So
like for instance,
hardware-wise, they actually turn on at about the same time.
Yeah. So why don't you have different timestamps, time durations for each of the motors?
Because if you go look at the Robo Rio, they flush the PWM outputs at a specific frequency. You go set your motors, it gets buffered, and then it gets executed. So the hardware locks you into a periodic tick. So we embrace that. We actually timed all of our control loops off the PWM cycle.
Are the motor controllers prioritized so that when they all wake up at the same time, who goes first?
On our software side, or on
Yes. Oh, this is all software.
We lump the ones that work together. So our ARM last year was solved in one process together.
Oh.
You put it in logical.
Multiple motors that were all in.
We lump it into logical units. Like the drivetrain stands on its own; it doesn't need to interact with the ARM. So you put the drivetrain on its own. The shooter was pretty independent, so we put that on its own, and then the rest of it
Does a logical unit get tested in software?
Yep.
Okay.
We test each logical unit. It's kind of whatever, like the ARM could hit the intake, so we wanted to test that.
Yeah.
So we simulate those all together, and then run those together in the same output. Anyone else have questions?
Do you ever have to take into account thermal effects when you do it?
This all comes down to how aggressive you make your control loops. So if we tried to push the limits on this and shave milliseconds off, we're going to start to have to tighten up all the gains and make our model more and more accurate and drive it harder. If you just don't drive your robot as hard, like when we looked at the plot and I saw the exponential decay and I said it was a time constant of say 0.1 seconds, I know from experience that's slow enough that I can ignore it, or that it will work. We're not trying to push the limits. So if you just stay away from the limits, you can ignore thermals and all sorts of other limitations. In practice, it's not a big deal. If we wanted, we could model, like we have a simulation now, we could model what happens if we lose a motor. We could model what happens if our motor gets weak or because it gets hot. Or we can model a lot of things and see if our loop's stable, which is actually pretty cool. In practice, we don't find an issue. Anyone else? Okay. Cool. Got lucky. Yeah, I'll stick around a while if you guys have more questions for me one-on-one.